Hello and welcome back to our program, applying the 7 steps of data analysis to produce a quantitative research study. William Bannon of StatsWhisperer here again. Okay, so in this presentation, we are also going to review step 6. However, this will be step 6 multivariate analysis for sample study 2. Specifically, we'll be using binary logistic regression to examine the joint effects of several predictors, those being our independent and covariate variables, on the categorical dependent variable, right? Our dichotomous dependent variable, happy, yes, no. From here, we will determine the strongest predictor of being happy, as well as determining the final levels of statistical significance for our predictors. Right? So recall, as we said last week, when you put all the predictors in a regression model, some remain statistically significant and some are no longer statistically significant. So they're significant at the bivariate level, but then when the joint effect of all the predictors are examined, some are no longer statistically significant. So that's referred to as our final statistical significance. Okay, so there are our 7 steps of data analysis. And once again, we are at step 6, multivariate analysis. You are here. So again, referring back to our data analysis parallel, this is the multi-data analysis. So this is where the bachelorette, after she's identified the bachelors with whom she has a significant one-on-one relationship with, determines who she has the strongest relationship with, and that bachelor gets a rose. Among, winning the show and going out on dates. So I guess that the rose might be inconsequential to him. But anyway, so step 6 in data analysis, the multivariate analysis, is about the same thing, right? So we're considering all the predictors that have a significant bivariate one-on-one relationship with the dependent variable happiness. And through multivariate analysis, we'll determine which of those predictors has the strongest relationship with happiness. If happiness could give a rose, it would give them to one of these predictors. So again, breaking down the term for multivariate analysis. Multi meaning many and var meaning variable. This is an analysis between many variables. Specifically, multi-many predictors, so multi-covariate independent variables, being regressed upon the dependent variable. So recall sample study 2, right? We want to be thorough here. Keep in mind what we're looking at. So on the left-hand side, we have our predictors, covariate variables 1 and 2, education and income level, along with the independent variable, do you live with a dog or a cat? And now the dependent variable is happy, yes, no, right? So each predictor is being compared with the dependent variable, happy, yes, no. Again, in our bivariate analysis, right, for sample study 2, bivariate analysis involved 3 independent tests to examine those significant one-on-one relationships. So a test between education level and happy, a test 2 between income level and happy, and test 3 between do you live with a dog or a cat and happy, yes, no. So here, in multivariate analysis, we are going to use one test, which is our binary logistic regression, right? So one test to compare the joint effects of all 3 predictors upon happy, yes, no. So again, multivariate analysis is going to answer some big questions. Again, 1, what's the final statistical significance between the covariate and independent variables with the dependent variables, which remain significantly related? 2, which predictor has the strongest relationship with the dependent variable? Right, so to perform multivariate analysis for sample study 2, we must refer to the multivariate test key. Right, so you may recall this from our last lesson. So how many tests do you need to perform multivariate analysis, step 6? Right, so essentially 3 when we're doing a cross-sectional analysis, which is an analysis with one measurement point. So 1, linear regression, 2, binary logistic regression, and 3, multinomial logistic regression. And do you recall how to determine which test to use? Right? This may look familiar, right? So we consider the structure of the dependent variable to determine which of the 3 tests are needed. And again, we're considering 3 variable structures. 1, the continuous dependent variable, such as happiness, measured on a scale of 1 to 5. 2, the categorical dependent variable with 2 categories, such as happiness, yes, no. And 3, the dependent variable with 3 or more categories, such as happiness, yes, no, somewhat. So we line them up in the multivariate test key with the dependent variable structures on the left and the regression test to use on the right. And if we plug in our sample variables, this is what we see, right? So if the dependent variables, happiness 1 to 5, continuous, we use linear regression, right? If it's happy, yes, no, right, which is our case here, we use binary logistic regression. Now, multinomial logistic, we're not going to review in this program, but that's what would be used if we were looking at happy in 3 categories, yes, no, or somewhat, as the dependent variable. So binary logistic regression, so it's going to tell us, is the study participant more likely to experience the dependent variable, happy, yes, no, by scores and categories of the predictors, right? Scores and categories among the covariate and independent variables. And of course, when we have a multivariate analysis, right, we're always mentioning while controlling for other significant influences on the dependent variable. So for example, is the study participant more likely to report being happy, right? Dependent variable equals yes, if she or he lives with a dog, so the predictor independent variable is dog, relative to a cat, while controlling for the other significant influences, education and income, upon the dependent variable. So that's exactly what we're looking at. So recall again, when using a categorical predictor with more than 2 categories, such as education level, each category must be dummy coded for use in the regression model. And again, if we see pages 204 to 212 of our 7 Steps of Data Analysis textbook, we see dummy coding, right? So as we said last class, if you recall, in our data entry week, we did recoding. So dummy coding is just another recoding process, right? So we're essentially recoding each category within the categorical variable to be separate dichotomous yes-no variables, right? For example, the variable education level is one variable with 3 categorical responses, right? So it's one variable that asks, what's your highest level of education? And your response choices are high school GED, or college, or graduate school, right? So that one item now becomes 3 dichotomous yes-no variables, right? So variable 1 would be education level high school GED, yes-no. Variable 2 is education level college, yes-no. And variable 3 is education level graduate school, yes-no. Now recall, we must leave one of these groups out In our regression model, so our binary logistic regression model here, we leave one of these groups out to make them the reference group. So the findings of the other two groups are in reference to the reference group, right? And again, if we have categorical variables that are already dichotomous, such as do you live with a cat or a dog, we don't need to modify those in any way because they're already dichotomous and therefore appropriate for use in our regression model. So here is our path to do binary logistic regression, right? So we have it all written down, but let's do it live. Okay, so here we are back in SPSS. So we go to Analyze. Of course, back to regression. Binary logistics, see, it's all right there. We click that. All right, here we are. So dependent, so just like linear regression, we put the dependent variable up here. So is the study participant happy? That goes up there. Now where it says covariates, that's where the predictor variables go, even the independent variable, although it's not a covariate variable. The thing to keep in mind with covariate and independent variables is in the regression models, linear and binary logistic, they're actually, processed the same, tested the same. The difference between them being in the independent and covariate variables is largely conceptual, right? It's just one is our variable of interest. However, as predictors, they're entered the same in the model. So of course, we leave out the reference group. So we leave out education high school. We put in education level college, education level graduate school. We put in our other covariate variable, income level. And then of course, we put in the independent variable, do you live with a dog or a cat? And we're all set up. Now, you must always remember to click options and the CI for exponent B, that's the odds ratio. So this is the 95% confidence interval, right, for the odds ratio. And this is always reported in just about every paper you'll ever see with an odds ratio. So you need this. Let me say continue. Now, we've dummy coded these variables here, right? So they're ready for use. But this option here is not available in linear regression, but it is in binary logistic. If you click categorical, you can actually move, say, if we had education level here with the 3 categories, we could move it over to the right and then select which is the reference group. So instead of dummy coding it, you could just put the single categorical variable here and just select if reference group is first or last if you don't feel like dummy coding these. However, we needed to dummy code these anyway for linear regression, so it all works out for us. So from here, we just click paste, right? And then we could highlight this and run it, and we get our output. Now, something worth mentioning is, you may recall when we did our linear regression, right, there was an option for the collinearity diagnostics to assess multicollinearity. Now, that's the one test assumption that we do need, right, for the binary logistic model. Now, there is no option to click collinearity diagnostics in the binary logistic regression model. So it's actually acceptable to use, right? So click OK, to use the values, right? The tolerance and VIF, the collinearity diagnostics. We could still use these values here in terms of correlated variables, even though this is a linear model, because the linear model doesn't matter what the dependent variable is because it's addressing the correlations in between the independent and covariate variables. So if you want to assess multicollinearity in binary logistic regression, you have to do the multicollinearity function in linear regression. And it doesn't really matter what the dependent variable is. It's kind of nice just to use happiness because it's another form of happy yes, no, but that's not necessary. So let us see our output for our binary logistic regression. So the first box you'll notice, a few boxes down in the output, is labeled omnibus tests of model coefficients. Now you look at this first because this indicates if the overall statistical model is statistically significant. And we can see it's less than 0.05, so it is. However, if it was not statistically significant, right, we wouldn't consider any of the characteristics of the rest of the output because we would consider all of those to be by chance. However, this is significant, so we will read on. So the next thing we could look at, right, so this is the coefficients box again. So there's an equivalent one from the linear regression, right, the coefficients box, where we look at the next dimension of the variable relationships, that being the statistical significance between each predictor variable and the dependent variable happy yes, no. Now you'll notice up here, right, so recall in the linear regression, they were all statistically significant, right? They were all 0.000. However, you can see for education level college, right, the significance is 0.732, so it's no longer statistically significant. And that happens many times when you change the structure of the dependent variable, like going from continuous to dichotomous, the relationship between the predictors change for the dependent variable. So when the dependent variable was continuous, right, happiness, 1 to 5, education college was significantly related, right? There was a significant difference between the education level of college in reference to high school GED, but now that the dependent variable is categorical, it's no longer significantly related, right? And that's what we mentioned also about final levels of statistical significance, right? So this might have been significant at the bivariate level, but now at the multivariate level, it's no longer significant. So in end, we would say it's not statistically significant. However, we do see that education graduate school is still significant. So that's significantly, different than the reference group high school GED. Income level remains statistically significant, as does living with a dog or a cat. So then we look at our next dimension of variable relationships, directionality, right? So we notice that there's only a minus sign for living with a dog or a cat. So the other betas are positive. So that means for education graduate school, they have a significantly greater, more than, right, likely chance of being happy relative to the reference group, education level, high school GED. Income is also positive, right? So if the higher the income, the more likely you are to be happy. Now living with a dog or a cat is negative, so we have to consider the coding again. So dog is 1 and cat is 2. So as the independent variable rises from 1 to 2, right, the likelihood of being happy, experiencing the outcome, which is happy yes, decreases, right, because of that negative sign. So as you go from dog to cat or living with a cat, your likelihood of being happy goes down. Now, this is very exciting. We're looking at our odds ratio effect sizes. Now, these are the effect sizes that everybody seems to like. These are the ones they even report on television because they're so communicable, right? So this is where, if you do X, you're 2 times likely to experience Y, right? So these are those, odds ratios, okay? So the first thing we see, the first odds ratio that's statistically significant is the education graduate school. And the odds ratio, which is the exponent beta EXPB, that's the odds ratio, is 23.85. So we would say that those with a graduate school education are almost 24 times more likely to be happy relative to the reference group, those with the high school GED level education, right? Almost 24 because it's 23.85. Now that's a very big odds ratio, and that's likely due, right, to our relatively small sample size, right? So the next one is income level. Now the interesting thing here is the exponent beta, the odds ratio is 1.04. However, it's not interpretable, right? So income level is continuous. So it's not appropriate to interpret that odds ratio the same as the categorical variables, say, in education level, right? So we would just say, right, that income level is, right, positively associated with being happy. Now, what's interesting is the lives with a dog or a cat, that odds ratio is actually 0.105. Now, it's easy to understand what almost 24 times more likely means, right, to be happy in the education example, but how do we interpret this 0.105 odds ratio? Right? Notice the minus in front of the beta, right, for the lives with dog or cat. That indicates a negative independent-dependent variable relationship, right? So the odds of experiencing the dependent variable, happy yes, decrease, right? So keep this in mind. An odds ratio below 1.0 is what the odds ratio you get when there's a negative relationship. So an odds ratio below 1.0 indicates a negative relationship, just like the minus in front of the beta. Now, negative odds ratios can be made clearer by converting the odds ratio by dividing it by 1, right? So if we divide 1 by the odds ratio, right, 1 divided by the odds ratio 0.105, we get 9.55, right? So that's a more easily interpretable odds ratio. Right, so thus we can say, right, thus data indicated that study participants that live with a dog are almost 10 times more likely to be happy yes, relative to those living with a cat, right? So by dividing 1 by the odds ratio, we have a more interpretable, right, number. Right, now, we also want to note the 95% confidence interval. Remember we checked the 95% CI, the exponent beta? So the confidence interval is telling us, what we're saying is this. We're saying that the odds ratios we have here probably aren't the actual odds ratios in the study population, right? But the 95% confidence interval is our way of saying, however, we're 95% confident that the actual odds ratios are between this lower bound and upper bound number, right? And of course, the smaller the interval, the more stable the finding. Now, when you have a relatively small sample like we have, the findings are a little less than stable, so you're going to see a wide spread in the 95% confidence interval. For example, our odds ratio with the graduate school, right, was 23.85. So the 95% confidence interval is saying that it could be in the population as low as 4.19, which is a medium size effect size, all the way up to 135.67. So that's a huge spread, right? So that presents, a less stable relationship. It's not our fault. It's a small sample. It's a limitation of small sample size, right? And then the odds ratio above it, you see the education college, you'll notice that includes 1.0 because it goes from 0.2 to 9.0. So it includes the 1.0. and it's not statistically significant, right? The significance is 0.732. So when the odds ratio includes 1.0, it includes the null value. Now recall, the null value indicates there's not a significant relationship, right, between the predictor and dependent variable. So you don't want 1.0 in the interval, because 1.0 is the SPSS's way of saying there could be no relationship at all. And usually when 1.0 is included in the 95% confidence interval, it's also not statistically significant. It's casting doubt both ways through the lack of statistical significance and the null value being in that confidence interval. So what did we identify here, right? So let's wrap it up. The multivariate model indicated, while controlling for education and income level, living with a dog or cat is related to the dependent variable happy, where those living with a dog are significantly more likely to be happy relative to those living with a cat. That is right, so that's our dimension 2, that's our directionality. So living with a dog, the direction more happy, right, more likely to be happy. At a statistically significant level, or dimension 1, with a large effect size, our third dimension of the variable relationship. So our accomplishment is, again, 1, we use statistical analysis to identify the significant influences on the dependent variable in bivariate analysis, right? What predicts being happy at a significant level. Then we use multivariate analysis to control for the significant influences while noting the independent and dependent variable relationship of interest. Then we identified at the multivariate level if there's a significant independent-dependent variable relationship with the directionality and the effect size, right? So we did quite a bit. Our next step is going to be communicating these findings to the world, right? Specifically in the next class, we're going to look at step 7, the write-up and report, right? We're going to report statistical analysis results in the proper professional format, right? For example, APA, AMA, we're going to talk about scientific language to report the results in text, as well as formatting and reporting the results in tables. Right, so there we are, all the way at the bottom now, step 7, the write-up and report for next week. Okay, thank you for watching, and I will be in touch with you the next class.